Hey everybody, it's Brian Evans with Sweatin' the Small Stuff. We're going to be doing a one-off here. I guess I'm sort of calling this a single drop of sweat. It's a little gross, I know, but I like that concept. It's always a little odd. It's a special one-off thing. We've got no Dan here, and I'm trying to do this as a video thing just to see how well I can do video podcasts of stuff to sort of expand what we're doing on the network here, because a lot of stuff that I do, it helps to actually visualize some of the things that I'm talking about, and so I'm going to try and get some video bits in here. So it's my first chance to do it nice and small, quick little story, just to see if it works. But Dan's off at Comic-Con because it's second week of July and Comic-Con's in full swing. It just started today. I'm doing 84 Charing Cross Road, so neither of us has any real time to get together to do this. But there was a story in the news recently that I wanted to talk about because it's right up my alley. It's about math, and the stories that I've seen about it don't actually describe the real issue of what happened. They give a very general overview, but they don't get into the details. And because it's kind of nitpicky and it's about math, and you're going to lose your readership. And that's precisely what I do on my show. So, Boston Museum of Science has an exhibit about mathematics that they've had for about 34 years now. And a 15-year-old who was visiting the museum, his name is Joseph Rosenfeld, saw their exhibit on the golden ratio and spotted what he thought was a mistake. And so he left a comment card with the concierge with his comments about the error, and a representative from the museum by the name of Elena Parks got back to him to say, quote, "You are right that the formula for the golden ratio is incorrect," unquote, and that the error would be corrected. But later, the spokesman for the museum, Erin Shannon, it's her name, spokeswoman for the museum, Erin Shannon, released a statement to say that no, they weren't wrong. Well, the problem is that everybody in this case was kind of wrong. Everyone was just a little bit wrong. Some more than others, but everyone was a little off on what was going on. Now, the various news stories that I'm seeing about this are saying that they're both right. But if we sweat the small stuff, we're going to find out that they're actually both wrong. And on top of that, a professor of mathematics at MIT got involved in this. His name is Arthur Maddock. He jumped into the fray and he said, quote, "The two numbers are the same, even if they look different," unquote. Well, that's not true at all. I don't know why. I mean, I think I understand why he was saying what it was that he was saying, but he was just completely wrong. And the reason that I think he was just misspeaking rather than misunderstanding is what he said after that. What he said after that was, the student is just presenting the fraction upside down. In other words, using the reciprocal number, unquote. And when you take that, you get the idea that he understands what he's talking about. He's just phrasing it so poorly that to say the two numbers are the same even though they look different. No, they're not the same because they're not the same. You just use them in similar situations. So how can this be? Can everybody be a little bit wrong and everybody be a little bit right? And what on earth is Maddock talking about with this discussion of reciprocals? Well, it has to do with ratios. Ratios are the relationship between two measurements. For if you have two things, how much bigger is one than the other? For example, every one that you have, I have two. But notice I can refer to that the other way. For every two that I have, you have one. It's the same ratio, just expressed in the other direction. Now, the thing about ratios is that you can express it as a single number. By dividing one side by the other, you get the multiplier to go from one to the other. So if we have a 1 to 2 ratio, then I take whatever you have and multiply it by 2, and that's what I have. But if we're going the other way with a 2 to 1 ratio, then it's the reciprocal. We take whatever I have, multiply it by a half, and that's what you have. So exactly what was the exhibit, and why did Rosenfeld think that this was a mistake? Well, it has to do with the golden ratio. Now, this was a proportion that the ancient Greeks and other cultures, not everything necessarily goes back to the Greeks, certainly for us in the West, everything goes back to the Greeks, used it as they thought it was an aesthetically pleasing ratio. And it is a way to have recursiveness of that ratio, is that the ratio builds upon itself to create the ratio in a smaller scale, which builds upon it to create it in a smaller scale. And similarly, you can go out the other way, where it has the ratio and it gets bigger to the same ratio, bigger to the same ratio, etc. Now, I'm going to get out my handy-dandy whiteboard here. And hopefully, with the glare of the computer, will not be showing up, and we'll have enough room here to be able to show everything that I want to do. Maybe someday I will have a lovely little stand because I won't be doing this at my computer desk here. So, you got a line segment. Suppose we have a little line segment right here. And it has a length of x. All right, now we're just going to divide it into two pieces there. And it doesn't really matter where we divide it, but we're just going to divide it so that we've got two pieces. And one of them we're going to call y, and the other one we're going to call z. So there we go. So now the golden ratio is such that the relationship between y and z is equal to the relationship between x and y. That is, the ratio of the parts is equal to the ratio of the larger part to the whole. This is that reciprocation thing. So the parts are to the whole, and the whole as the parts are to each other. And thus you can get down in there. So, what is that ratio? Well, it's the Greek letter phi. It's been used so often, it's been given its own little constant number like pi or e. And it happens to be equal to, approximately, since I don't have anything, 1.618 ... And it's this infinitely repeating number that goes on and on and on. So, how do we calculate it? I mean, it's all well and good for me to just tell you that that's what it is, but how do we calculate that? Now, to figure that out, we need some algebra, and we need the quadratic equation. So we're going to go back to our example. So we're going to calculate this out here. We've got the length is equal to the sum of its parts. So x is equal to y plus z. That's very, very simple, very straightforward from the example that we've got. But we want to figure out how to cut it so the length of the smaller piece, z, when multiplied by the ratio phi, is the same length as the bigger piece. And if we multiply the bigger piece by that same ratio, it'll be the same as the length of the whole. So therefore, we want y to be equal to phi, whatever it may happen to be, times z, and we want x to be equal to phi, whatever it may be, times y. Those are little bits. So we take z and we multiply it by phi and we get y. Then we take y and we multiply it by phi and we get x. So what we need to do is start substituting these values in for each other, and that way we can get a single formula all in one variable, which we can then solve for, because a single variable and a single unknown is solvable. So we know that x equals phi y. So we can substitute that in for z. We can substitute the z phi in for y. So if x equals phi y and y equals phi z, then x equals phi times z, or, which is equal to z phi squared, is what we've got there. So far, so good? Good. Thus, if we go back to our first equation, x equals y plus z, then we can substitute it in there. So x equals, so if x equals z phi squared, then that is going to be, so we've got z phi squared equals y plus z, right? So far, we've gotten rid of the x by casting it in terms of z. But now we're going to want to get rid of the y and get everything in terms of z. Well, y is just equal to phi z. So therefore, this is equal to phi z plus z. Or if we combine all the terms on one side, we take this and we move it over here to this side, we get, I'm going to go back up here because I'm kind of running out of space, I can see, we've got z phi squared minus z phi minus z equals 0. That's a single equation in a single unknown. Now, if you know anything about the quadratic formula, you can see where this is going, because this is something that we can actually solve for. And if you recall, suppose you have an equation of the form ax squared plus bx plus c equals 0. Well, the quadratic equation solves that. We may get into that in another show, but for right now, hopefully everybody remembers their algebra, where x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So all we need to do is for this, in this case, a. So what we're going to do here is here's just an example to prove, just in case you don't believe me, here's an example to actually prove that. So suppose we've got 3x squared minus 2x minus 5 equals 0. Okay? So I'm going to get rid of all this other stuff because that's my old work, and I'm running out of space on my little board here. As professors are always want to do, they erase what it is that you're writing down in your notes. So we're going to figure this out. So x, so in this case, this is a, this minus 2 is b, and this minus 5 is c. We're going to pull that back into this equation up there. So in this case, x will be equal to minus b. So it's minus 2, okay, plus or minus the square root of, divide that there, so we got there, b squared, so that's minus 2 squared minus 4 times a, which is 3, times b, c, which is minus 5, all over 2 times a, which is 2 times 3. So we're going to count this out. Minus 2 is 2, plus or minus the square root of minus 2 squared is 4. So 4 times 3 is 12, times minus 5 is minus 60, but minus 60 makes it plus 60 all over 6, which means that we've got, which is equal to 2 plus or minus the square root of 64 over 6, which is equal to 2 plus or minus 8 over 6. So in other words, it is either 10 over 6, which is equal to 5/3, or it is minus 6 over 6, which is equal to minus 1. Those are our two answers there. So we've got 5/3 or minus 1. And if we plug them back into this formula, you'll see that it actually works. Let me prop this up a little bit here. So 3 times 5/3 squared minus 2 times 5/3 minus 5. Well, that's 25 over 9 times 3. So that's 25/3 minus 2 times that is 10/3 minus 5. Well, 25 minus 10 is 15. Over 3 is 5, which is 5 minus 5 equals 0. So therefore, we know that this is an actual correct answer to the thing. But we can substitute minus 1 in there as well. So we'll erase that, and we'll do it in. So 3 times minus 1 squared minus 2 times minus 1 minus 5. Well, minus 1 squared is 1, so this is 3. Minus 2 times minus 1 is 2, so this is actually plus 2 minus 5. And as you can see, 3 plus 2 is 5, minus 5 equals 0. And congratulations, that's the answer. So either one of these two answers will solve this equation. So we need to figure out what is phi for up there. And if you're paying attention, you can already see where this is going. Now here's the part that some of you might balk at. And I hope you can trust me that this is going to be okay. We're going to take z here, and we're just going to arbitrarily say that z equals 1. Because it doesn't really matter. we're dealing with ratios. For every one that you have, we're going to multiply it by this ratio in order to get the other pieces out of there. So we might as well start with 1. We could do it with a half. It's just going to make the math that much more difficult if we do it that way. So we're just going to start off with 1. So with z equals 1, then we've got a equals 1, b equals minus 1, and c equals minus 1. So we set up our equation. So phi is equal to minus b minus 1. Because I know I'm going to run into them over there. So z equals 1, and we're going to have, so a equals 1, b equals minus 1, c equals minus 1. So we have minus 1 plus or minus the square root of 4, square root of b squared, so that's minus 1 squared minus 4 times a, which is 1, times c, which is minus 1, all over 2a, which is 2 times 1. So let's start calculating that out. Minus 1 equals 1, plus or minus the square root of minus 1 squared is 1. So we have minus 4 times 1 times minus 1, which is equal to plus 4 all over 2. And so therefore phi equals 1 plus or minus the square root of 5 over 2. That's how we calculate what it is. So if you actually calculate this out, you're going to find that, let's take the plus version. So 1 plus the square root of 5. Now the square root of 5 is approximately 2.236. So the square root of 5 is about 2.236. 1 plus that is equal to 3.236. And if we divide that by 2, 2 into 3 is 1. Carry the 1 over. That's 12. Divided by 2 is 6. 3 is 1. 6, 8. 8, not 6. So 1.618, and it goes on, and so therefore you can deal with that. So that's phi, 1.618. That's the number that I told you about to begin with. I apologize for the video jump there. I realized as I was going through that I had wandered off onto a really weird tangent that I really didn't want to get into. So we just calculated that phi is equal to 1 plus or minus the square root of 5 over 2. Now, this is where I get off at saying everybody was sort of kind of wrong about what was going on here, because what the museum had done is that they were talking about the golden ratio in terms of a rectangle, and that's a very common thing. That's what the Greeks were dealing with it, because the reason that they feel this is so aesthetic is that if you have a rectangle such that the sides of the rectangle are in proportion to this golden ratio, then the rectangle, it doesn't look too long and skinny, it doesn't look too much, like slightly off square. It's this lovely little sort of ratio about it, such that the ratio of this side, x, and this side, y, if they're in proportion to this golden ratio, it's a nice looking rectangle. Now the thing is, because you'll notice that in this phi it's 1 plus or minus the square root of 5 over 2. Well, since the square root of 5 is about 2 point, stuff, that means that the other possible version of phi is a negative number. And negative numbers really aren't exactly what we're dealing with when we're talking about phi and these ratios there. I mean, it solves this equation, but you don't multiply length by a negative number, because what's a negative length? I mean, it's kind of this is your subtracting, but you end up with a negative number when you use it in calculation. So we don't really use the negative version of this equation. We just use 1 plus square root of 5 over 2. The thing is, what the museum had done was that they had presented this thing, and rather than doing their division of the long side divided by the short side, which would indeed be 1, my pen is running out, plus square root of 5. Oh, come on, pen, over 2. Let's see if I can find a better pen, because apparently my purple pen is running out. So let me go with my blue pen. Hopefully my blue pen will deal with that. So rather than doing this way, and so you can have, 1 plus the square root of 5 over 2. So that's the normal identity as to what phi is. It's not plus or minus. We'll just use the plus version of it. That's what we want for phi. What they had shown on their board was square root of 5 minus 1 over 2, which they said equals phi. Now, if you calculate this out, square root of 5 minus 1 over 2, that is, let me get my notes up here. So I've got 2.236 minus 1 equals 1.236. And if you divide that by 2, it's equal to 0.618. Now, one of the nice things about this thing, is kind of interesting as a number, is that phi equals 1.618, and 1 over phi equals 0.618. So 1 plus the square root of 5 over 2 gives you phi. If you sort of reverse it and negate it, square root of 5 minus 1 over 2, you don't get phi, you get 1 over phi. It's really kind of interesting. This is one of the nice things about phi, is that it's related to its own reciprocal in a bizarre sort of way. And this is one of the really interesting things about it. But this is why Rosenblatt thought that there was a problem, because he is indeed correct. There is a problem. Square root of 5 minus 1 over 2 isn't phi. It's 1 over phi. But it really is, it's over y. If you take the short side divided by the long side, you get the reciprocal of the long side divided by the short side. Long over short, y, in this case, y, let's see how we got some room. So y over x equals phi. X over y equals 1 over phi. And that's where the problem is. He was saying you just needed to change this square root of 5 minus 1 into square root of 5 plus 1, and then you'd be correct, because then it would say that. The problem is, that's not what they were talking about. They were talking about this other thing. So he was very close to being correct. Really, really close, at least according to the news story. I don't know what he actually wrote to these people. So to Rosenfeld, if you did point out that they were dividing by the wrong side and thus got the wrong equation for phi, then that would have been absolutely correct. But the museum, in their response, saying that, yes, we will fix this by making the minus a plus. Yeah, but that doesn't solve the problem, because you're still working with the wrong example for the equation that you're coming up with. And then that gets into the mathematician, because he was trying to say, well, these two numbers are the same. That these two numbers are the same thing. They're just written differently. No, they're not. They're different. The reason that they're written differently is because they are indeed different numbers. One is the reciprocal of the other. And unless you're one, the reciprocal of a number is not the same number. So, this is what sort of needs to be done for the exhibit. They need to, probably the best thing, I have a couple things about what it is that they can do. One, change the description of what they're talking about to have not the short over the long, but rather to have the long over the short, and then convert their equation from square root of 5 minus 1 to square root of 5 plus 1, and that'll make it correct. The thing is, it's this plaque, like I said, it's 34 years old. They got to be very careful about it. Museums, you want to make sure that you're not destroying the exhibit that you're dealing with. But the other thing that they could do is to change the formula. So they can keep everything the same, and rather than saying, let me get rid of all this other stuff that's kind of in the way. So rather than saying the square root of 5 minus 1 over 2 equals phi, they could say the square root of 5 minus 1 equals 1 over phi. The problem is, that's not really a very satisfying result, because when you're dealing with the golden ratio, you're dealing with phi, not 1 over phi. You're dealing with phi. Phi is the way that it's the number that we're using, and so therefore if you're trying to display that number, you want to give an example that results in the number that you're dealing with, not some bizarre calculated reciprocal version of it. So what they need to do is say, talk about the long side of the short side, make this +1, and then everything will be great. So that's it for this week. Hope you had fun with this one. This will be a little bit shorter than some of the other bits where I've ranted on for an hour and a half. But until next time, this is Brian Evans with Sweatin' the Small Stuff, where the devil is in the details.